Hello and welcome back. I'd like to do another lesson on hypothesis testing for the mean with large samples, but we're going to do it a little bit differently this time. And that little bit of different is coming in the decision rule. So last time we were doing the decision rule and we were working with p-values, but there's another approach to the decision rule besides p-values, which we call critical values. So let me show you how these work. The formula is going to stay the same, x bar minus mu divided by sigma divided by the square root of n. But to show you critical values, we're going to start with a right-tailed test at the 0.05 significance level. Now you'll recall when we were working with p-values that 0.05 significance level corresponded to a 0.05 rejection region in a right-tailed test. That means it's up at the top. The question becomes, though, what z-value is this? Well, if there's 0.05 at the top, that means to the left of that line, or z-value, is 95% of the curve. Well, using your calculator or software, we can figure out what that z-value is. On the TI 83 or 84, we'd go down to second bars, inverse norm, plug in 0.95, and it brings up a z-value of 1.645. This is what we call a critical z-value. Let me show you another one. Still at the 0.05 significance level, let's look at a two-tailed test. Again, the two-tailed test splits that significance level into a lower and upper half, 0.025 on the bottom, 0.025 on the top, still 0.95 in the middle. So what z-values are these? Well, let's pull up the calculator again. And this time we're going to put in an area of 0.025 into the inverse norm. And it tells me that the z-value on the bottom is negative 1.96. And we can mirror that onto the top. So we have two critical values now, z equals plus or minus 1.96. If we continue this process for right-tailed, left-tailed, two-tailed, and each of the significance levels, what we would find is the most used critical values for z-distributions when we're doing hypothesis testing for means. Again, we have a right-tailed, left-tailed, and two-tailed tests. And this is what their hypotheses look like. And we can make ourselves this little chart so we can always just glance at it to see what the critical z-values are. Now, if you have time, just pause this for a moment and see if you can find the missing critical z-values. If you don't have time, well, here they are. So let's put this into use and I'll show you how they work. Teachers in a local school district claim that the mean salary of the district's teachers is less than that of the neighboring district, which is $47,000. A random sample of 34 teachers has a mean salary of $46,000 with a standard deviation of 5150. At alpha equals 0.05, test the teacher's claim using critical values. The hypotheses, well, we set those up the same way we always have. Our null in this case is mu is greater than or equal to 47,000. Our alternate is that mu is less than 47,000. Our significance level is 0.05, and we're doing a left-tailed test. So let's bring up our left-tailed chart. If we have an alpha of 0.05, that means our critical z-value is negative 1.645. So this is what the decision rule would look like. If z is less than that negative 1.645, we'll reject the null. But if it's greater than negative 1.645, we'll fail to reject the null. So let's see what happens. We put all that information into our formula, and we get a z-value of negative 1.13. So since negative 1.13 is greater than negative 1.645, we'll fail to reject the null. So we're accepting the null, which means that the mean salary of the local district could be more than or equal to $47,000. Let's try another one. The U.S. Department of Agriculture reports that the mean cost of raising a child from birth to age 17 is about $233,610. Wow, you hope this value is incorrect. So you select a random sample of 750 17-year-olds and find that the mean cost of raising them was 232,988, with a standard deviation of 7,590. At alpha equals 0.05, is there enough evidence to conclude that the mean cost is different than $233,610? We're going to use critical values. So our null in this case is that mu equals 233,610. The alternate is that mu doesn't equal 233,610. Our alpha level is 0.5, and we're doing a two-tailed test. So we'll pull up our two-tailed chart. And at 0.5, we've got two critical values, a positive and a negative 1.96. So this is what it looks like in the decision rule. If z is less than negative 1.96 or greater than positive 1.96, then we'll reject the null. However, if z is between those two values, we'll fail to reject the null. So let's see what happens. Plug it all into our formula and we get a z value of negative 2.22. That's less than negative 1.96, so we reject the null, which means that the mean cost of raising a child from birth to 17 is likely different than $233,610. So that's a different approach to hypothesis testing for the mean. Instead of p-values, we're using critical values. Thanks for being here.